Okay. Today was my last day of teaching those kids. So I feel like I've been paroled from prison. All right. So last time we had finished up, I think, or maybe the time before, but we had finished up our calculation of the one loop corrections, and we talked. So we had talked about how to incorporate those and compute the one loop corrections or the next leading order corrections to the scattering process. So phi phi goes to phi phi in this phi cube theory, right? And the way we did that was we compute first, the exact propagator and the exact vertex. It's not the exact, but it's as exact as we can get it at this point, which is a one loop correction, along with the loop-induced 4-point vertex, right? And so we said, well, we start by writing down the tree level diagrams, and then we plug in those guys, right? And we expand out, the exact propagator and those exact vertices, and we keep the order alpha corrections, okay? And so that's what we did, and we got some really nasty looking thing, right? And then we said, well, what can we do with this? Let's try to, work in what we call the massless limit, right? And this is a good limit, especially when you consider, the scattering energies that are typically involved in these types of experiments. So that, like the LHC, you're at 14 TeV, and the masses, you're talking about, especially if you're talking about QCD cross sections, you're talking about, quarks that are basically massless, gluons that are exactly massless, and so it's a good approximation. So that's what we did. So we took the mass to 0, and we found that a lot of terms simplified, and we got it down to the one loop amplitude to look like this. So here's our tree level amplitude, right? And here's the order alpha corrections. So it factorizes into, some factor alpha times a log, multiplying the tree level amplitude, right? And we said, all right, cool, we're patting ourselves on the back, and then we say, wait a minute, we've got this term here, S over M squared, right? So if we take M to be 0, this log is going to blow up, and what it's going to do is not only, is it going to get big, but it means that our perturbative expansion, the whole idea of perturbation theory is breaking down, right? Because the next leading order term is going to dominate, right, over the tree level diagram, and that goes against all, our whole assumption. And so this was something that we had swept under the rug when we first did this, but we're confronted with this. Our experimental friends, we go and compare our numbers to what they measure, and we find that we were off. Okay, and so our experimental friends are like, well, wait a minute, how can you have this log of S over M squared term when you've taken the massless limit, right? And then we're like, all right, crap, I guess we got to deal with it, okay? And so then at that point, it's a lot like coding. It's a lot like programming. If you've ever programmed, when your code doesn't work, you go and look at the places where you have a high probability of making a mistake, okay? And so one of the things that we realized that we didn't do was we didn't account for the fact that, in the real world, detectors have limitations, okay? So it could either be, some energy threshold that we can't measure, particles hitting the detector below some energy, or it could be the fact that these particles are very close, or two of the particles are very close when they hit the detector, and it looks like, just one particle, right? So in other words, we needed to account for the possibility that particles could radiate off another particle, and that guy could be either soft or it could be collinear, right? And so that's what we did. We worked on computing the contribution from that type of process. It involved a couple of tricks, but we were able to not only compute that process, but see the way in which this massless limit's breaking down in particular, so in the for the real corrections, how it breaks down in the massless limit, or how we get these soft or collinear pieces, right? Because the whole amplitude or amplitude squared went like 1 over this stuff, right? We said if omega is small, if it starts going to 0, then the amplitude is going to blow up. And if they're collinear, if theta, the angle between two particles, goes to 0, then that obviously is going to blow up because sine squared is going to be 0. All right. And so we said, okay, so then we said, all right, we're on to something here. We're computing these real corrections, and we're seeing that there's some divergent behavior. Hopefully, this is going to be the cure-all, right? It's going to give us the same type of terms with minus signs, and everything's going to cancel off. We can go home and be happy, right? And so we looked at, in particular, in general, d dimensions, and we see that if we work in 4 dimensions, we're going to have both soft and collinear divergences. Luckily for us, we're working in 6 dimensions, and so we only have the collinear divergence to work with. Okay, but in the real world, in 4 dimensions, you typically have both, and you have to deal with both. And so we were asking, are these hopefully the same divergences? And so we're saying, let's in our computation, when we integrate over these final state momenta, let's put in some limitations. Okay, so we'll put in a limitation on the energy threshold, put a limitation on, well, we don't have to put energy threshold in 6 dimensions. So in our case, we just have to worry about the angular, right? The angular acceptance, or angular threshold. And so we introduced some new parameter that we call delta, and we're assuming it's much smaller than 1, but it's still a lot bigger than these mass terms. All right, so where did we get to? So we went through some computations. We got it down to a point, so we expanded. We introduced this notation where K1 and K2, which are the momenta of the 2 splitting particles, we wrote those in terms of the original momentum by introducing this parameter called x. And that allowed us to kind of whittle it down to the amplitude squared being a function, or 2 intervals, 1 over x and 1 over theta, which is the angular separation between these 2 particles. And it turns out that we could do those integrals. And what we ended up getting was something that looks like that t observed squared there in the middle, right, where c is just some constant. Okay, but this was just for one diagram, and in fact, we have to include the radiation off of all 4 external legs, and then once we do that, it just gives us a factor of 4, right? And so we end up with something that looks like that. Okay, it looks like there's some s over m squared dependence. Okay, so that part of it looks good. Part of it doesn't look good is that we've got this dependence on delta squared. But when we add it together with our virtual corrections, we get some cancellation, but the log of s over m squared is still there. Okay? And so we still have our big log, and in fact, our large logarithm problem now has doubled, right? Because now we have this guy, but we also have this guy, because this is some small angular resolution, and so it also blows up as well. Okay, so we've doubled the problem, okay, or doubled the number of large logs that we have to deal with. All right, so the thing that's telling this is, I don't know if I pointed this out last time. So the thing is, you build a really good detector where you can get really good angular resolution, and that means that this term's blowing up, right? But what it's telling us as theorists is, now we need to match the precision of the experimentalists. We have to go to one higher order in the perturbative expansion. Okay. Okay. So we still have these 2 poles, and now we want to try to deal with them. This guy. Okay, and let me see if anybody gets my joke here. First slide. Whatever starts. Okay, take a second and look at that. Anybody?
Tunguska?
No,
I didn't get
it's a log jam, but it's blowing up. It's logs that are blowing up. Okay.
Spoiler alert in the caption.
Yeah. Yeah, if you could see that, then.
Oh, yeah, I didn't see that.
Okay. So what I want to do is talk about other renormalization schemes, in particular one called MS bar scheme, and we'll start to get into what's called the renormalization group. Okay. All right. So let's see where we are. So okay. So we up until this point, we've computed the one loop amplitude. We've computed this real corrections, right? And when we put them together, we ended up finding that we still have the original log that is a problem in the massless limit, and we have this log from the real corrections, right? And that one from the real corrections I'm going to set aside for the time being. And let's just look at trying to cancel off or trying to figure out where we went wrong. Why do we have this log that's blowing up? Okay? And so what we're going to do, what we're assuming is that somewhere we made a conceptual mistake. Somewhere along the way, either when we did the calculation or we did the renormalization or we took the limit, somewhere we screwed up. Okay? Or somewhere we didn't, we just didn't catch something. Okay? All right, so what we're going to do is let's go back and look at the one loop corrections to the self energy. Okay, so we had the tree level, the one loop, and the counter term. Right? And I can write the exact propagator, like we said, in terms of the tree level propagator. Right, the first term is this tree level. Second term is where we cut off basically the two external propagators, and what's left in the middle is the self energy. Right, and we're not going to go through the whole calculation again. Just write down the answer. So this is what we found, right? And D is some complicated function of x and k squared and m squared, okay? And so what we did was at this point, we did everything we did was sound. We didn't make any mistakes. We went and checked all our factors of 2 and pi's and all that crap. And it all looks good, right? And so we said, okay, well, now we know that at this point, for the LSZ formula to be valid, we have to satisfy those two conditions, but the VEV being 0 and the one particle states having the correct renormalization. And that is, you can reformulate that and say, well, the condition that we need is that the exact propagator has a pole at m squared with residue 1, right? When we apply the residue theorem. And that means that when I apply the on-shell conditions, when I take the external momentum k squared equal to the mass squared, the self-energy correction has to be 0. And also, we have to apply the condition on the derivative of this guy, that when we apply k squared equals m squared, this thing has to vanish, right? And the derivative, I've written it out there. I don't know if we wrote it out explicitly last time. Okay. But to do that, we said, okay, well, in order for that to be satisfied, right, when I set k squared equal to m squared, and I want the self-energy to be 0, that leaves me with this, right? A and B have to be this, okay? They have to, because we wanted to cancel off the pole, we wanted to cancel off the dependence on this unnatural scale that we introduced, right, this mu scale. And then we allow for the fact that A and B can be contain some constant terms. Right? And the denominator. Okay, so this was all when we had finite mass, and then we took the massless limit, right? Okay, and that's where, and then we went off and did everything we did. Okay, but now let's go back and let's think about this in the massless limit. Okay, let's just think. So we went off and computed the cross section, or the amplitude squared for phi scattering. Let's just stay with this self energy thing for a minute. Okay, and let me take the massless limit. Okay, so that means that the denominator had that had that minus m squared term. Well, that's gone now. Okay, so I've got the denominator there, right? And so when we now, we take our expression that we computed for the self-energy and we want to renormalize it, right? We want to apply those same conditions, right? But now k squared is not m squared because m squared is 0. So now I'm setting k squared to 0 in both the self-energy and its derivative. Right? And what we find when we do that is, if we look back, in this term right here, you can see that we're going to run into some problems because d, which now is just that 1 minus, or x times 1 minus x times k squared, when I set k squared to 0, I've got log of 0. And I'm not a mathematician, but that's a bad thing. Okay? So these things are ill-defined. When we take the massless limit of just the self-energy expression that we get something that's ill-defined.
Log 0, I guess, goes to minus infinity.
Yeah. So we don't have something that's well-defined. Yeah. Right. The self-energy is blowing up and the derivative is ill-defined, right? Okay. So we see this could be our light bulb moment, right? We see, okay, there's something funny going on here, right? When I've computed the self-energy and I take the massless limit and I try to apply these conditions on the self-energy, that's when things go haywire, right? And so that gives us a light bulb moment. Okay, so now we're saying, okay, wait a minute, maybe we're doing something wrong when we renormalize, right? When we do the subtraction, okay. All right, and maybe this choice of what scheme we use, maybe there's a different choice as far as how we renormalize. Maybe that in the massless limit will do away with these logs. Okay. All right, we'll see how it works. Okay. So what we're going to do now is try the minimal subtraction that you can do. Okay, which is the minimal subtraction you can do. You know that when you compute that self-energy, you at least want to cancel off the poles, right? At the least, you want to cancel off the poles. You don't want things blowing up, right? You don't want divergences in there because then experimentalists are pointing them out to you and you feel like an asshole, okay? So we at least want to cancel off the poles, okay? So that means that, let me go back, and in this massless limit, just kill off the poles, okay? So just set A and B to just be enough to kill off the poles, okay? So in other words, we're leaving the mu dependence and we're leaving all the constants the way they are, okay? And this is called, it's called the modified minimal subtraction scheme, or MS bar is what I'll be calling it. It's called modified because minimal subtraction was the first attempt at this, and minimal subtraction you cancel off the poles and the mu dependence. So the modified, the MS bar, is you just cancel off the poles. Okay. So nobody uses MS, everybody uses MS bar, okay? All right. So the renormalization scheme that we used before, I think I told you this, but it's called, in the business, it's called the on-shell scheme, okay, or a wet scheme, all right? All right, so let's see what happens. Oops. Okay. So let's see what happens. Okay, so we're in the massless limit. Okay, we have we've set A and B to just cancel off the poles. Right. So in the top part you have the self-energy in the MS bar scheme, and then the bottom has that one that we have we've written down before, where A and B are also canceling off the mu dependence. So you can see the difference. At first glance, they kind of look the same, but you can see the differences in that top one. I've still got mu dependence, right? Okay, and there's the definitions of T0 and D. Okay, so we haven't talked about applying the renormalization or applying the the condition of the physical pole and the residue yet. But let's just cancel off the poles, okay? So here's a comparison between the two, okay? You guys watch Jimmy Fallon?
Yeah.
Everybody watch Jimmy Fallon? So he has a skit where he does
Yeah,
pros and
pros
cons.
and cons.
Okay? So here's the pros and cons of on-shell and MS bar, okay? So on-shell, we've already seen that the pro is we cancel off the poles, and it's also independent of mu, right? The bad thing is, the con is that when we take m to 0, we can have these logs blowing up, right? In MS bar, we've seen that, or we will see that it's going to be well behaved in the mass goes to 0 limit, okay? I'm kind of giving away the spoiler, but it's going to be well behaved. The bad part is it's going to have some dependence on this fake parameter, this unphysical scale that we introduced, okay? But we'll see how to deal with that in a minute. Okay, so if we decide to use MS bar instead of on-shell, what does all of this mean for, our calculations that we've done? Okay, so the first thing is it means that the exact propagator is not going to have the simple pole at m squared with residue 1 anymore. Okay, because we're not, we're not, when we set the self energy, when we apply those conditions to the self energy, it's not going to be 0 anymore. Right? And so there's going to be corrections to what we would call the physical mass. Okay, so the pole is going to now occur at not m, the Lagrangian parameter, but m physical. Right? M physical is going to have some dependence on alpha and mu. Okay. All right, but we've said all along that we had to have that be satisfied, those conditions be satisfied in order to use the LSZ formula. Okay. So if you're playing a game and you don't like the rules of the game, just change the rules, right? So that's what we're going to do, okay? So instead of trying to figure out how to fit something in within these, constraints of the LSZ formula, let's see what we can do with the LSZ formula to fit, what we want, okay? Make sense? Okay. All right, so we need to make some adjustments, okay? And the way we're going to do that is we're going to multiply the right-hand side of equation 15 by this factor of 1 over the square root of r, where r is our residue. Okay, so remember, the residue is not necessarily 1 anymore, so let's basically normalize the right-hand side. Okay, and so what that means is that when we compute the one particle state, the normalization, that this guy now has to have a unit amplitude. Okay? So in other words, instead of phi, now we're going to have r, 1 over r squared, the square root of r times phi being giving us the unit amplitude. Okay, and also so this corrects for the fact that we don't have a residue of 1. And then to correct for the fact that we don't have the simple pole anymore at m squared, we can just try to replace everywhere we have m squared here, replace it with the physical mass squared. Okay? So we're doctoring up the LSZ formula to fit our needs. Okay? So like I said, we're forcing all external momenta to obey not the on-shell condition, k squared equals m squared, but we're forcing it to obey k squared equals the physical mass squared, right? Right, and so if you want to get technical, or if you want to understand the details, you go back to the how we derive the LSZ formula and put these changes in, and you'll see how it all works out. Okay, I'm just going to sketch it here because it's not that important for our purposes. Okay, so what do we have? So we have it's going to give us changes to our Feynman rules, right? So what we'll see is that each external line, if we went back to the LSZ formula and we do our derivation again, we're going to see that each external line is going to carry a factor of r. Okay, we'll have for every field in the term, we'll have a correction of 1 over the square root of r, and what do we say? We get a net, so we get a net factor of the square root of r for each external line when using MS bar, right? Let me think how that works. So each external line contributes a factor of r. It's the external propagator. This is my center. I can line up the correction from each field. Right. Okay, so what all this is telling us is that when we make those changes, right, we're going to get a net factor of the square root of r. And so what we'll do is, to incorporate that, we'll incorporate it into our Feynman rules. Okay. And we'll see how that works in just a second. Right. So when we do this, it's all we're doing is changing the Feynman rules a little bit. Okay. The physics should still be the same. The internal propagator and the vertex, they keep their same form, so we don't make any changes to those guys. But we do note that the mass parameter in the Lagrangian is, or in the propagator, is the Lagrangian parameter. Okay, because if we use the physical mass square here, it would actually be part of the next to next. It would be part of the next to next to leading order corrections, right? If you think about what we have so far, we've got m physical squared. It's m squared plus some order alpha corrections, right? And if I plugged in m physical squared here, I could expand in this guy, right? And I'm going to get parts of this that are going to hit our order alpha corrections. So it's going to be higher order. So we can just, at this point in the propagators, we can replace m physical squared with m squared. So first I replace m squared with m physical squared, and then I replace m physical squared with m squared. It's like the shell game. Yeah, the on shell game. Okay, so let's try it. So let me do this in a little more detail, and hopefully it'll be clear. Oops. Okay, so let's look at the propagator, the exact propagator, but it's a little easier to look at the inverse. Okay, so I've got k squared minus m squared, and then I've got the contributions from self-energy and MS bar. Right? And we've seen that when we set k squared equals z squared, that guy is not going to be 0. Okay? But if we set k squared equal to m physical squared, which is those two terms, we should get that the inverse of the propagator vanishes. In other words, there's a pole there. Okay? So if we combine these two observations, we can write down that that m physical squared minus m squared minus the self-energy corrections should be 0. Or if I move some stuff around, m physical squared, like I said, is the Lagrangian parameter mass squared plus some corrections from self-energy. Okay, and the difference is terms of order alpha, like I was saying here. Okay, so in other words, what we can do is when we compute this guy and we set k squared to m physical squared, we can actually just use the Lagrangian mass parameter, because the changes, you would have some dependence on the self-energy here inside, and so when you expand it, you'd actually get higher order corrections. Okay, so you can just replace m physical squared with the Lagrangian mass parameter squared. Okay. So let's take that and plug it in for what we had earlier. Make sure plugging this into equation 18. So let me plug in for m physical squared there, that stuff. Right? And so now I have m physical squared, and the self-energy on the right-hand side just depends on so everything on the right-hand side just depends on the Lagrangian mass parameter. Okay? And if I plug in the expression for the self-energy in the MS bar scheme, I get something that looks like that in the box. Okay? Okay. So we've got an expression, a relationship between what we're calling the physical mass, what we would measure at the, at the experiment, and what the mass parameter in our theory. Okay? And the first thing we see, like we said, is that in MS bar, we've got explicit dependence on the mu scale. Right? And that's not a good thing because we have no idea what this mu scale is. We just put it in because we were trying to keep the coupling to be to not have a mass dimension, right? Because we said any couplings with mass dimensions, a lot of times you run into troubles, right, with normalizability. Okay, so we got to figure out what's going on, right? The only thing that would make, or that would, how do I want to say this? So this is where you have to take a leap of faith, okay? So we know that m physical squared is what it is. We measure it, it is what it is, right? And the only way that would change, the only way that would be true is as we vary mu, is if m, the bare Lagrangian parameter, and alpha take on different values, take on different numerical values, right? Because you need those guys to somehow counterbalance the change in mu, right? So you need those guys to depend on mu so that when you vary mu, everything on the right-hand side doesn't depend on mu. Okay, does that make sense? What I'm saying?
I think
okay. All right. We'll see how it works, okay? Or just accept it, okay? So in other words, we want m physical squared to be a number, okay, that doesn't depend on mu because it's an observable. So that means that our Lagrangian parameters, m and alpha, or the g, the coupling, they have to depend on mu, right? And so what we want to do is try to figure out what that mu dependence is. Okay, and we can actually use, this information. I call it information, but you might call it a leap of faith, right? Because you're saying, this is, I computed this thing, it's got this mu dependence, but I know it can't depend on mu, so, I've got these parameters I can play with, maybe they depend on mu, okay? So you can say, okay, let's see if we can figure out what this dependence is, right? And the first thing you want to do is take a natural log of both sides, okay? And we'll divide by 2. So let's look at this real quick. So I'm taking the natural log of equation 20 and divide by 2, right? So, okay, so there's a couple steps here. So I'm taking the natural log. The left-hand side is obviously 2 times the natural log of m physical, right? On the right-hand side, I've got the log of 2 quantities, right? So I use that thing that says the log of 2 quantities is log of 1 quantity plus the log of the other quantity. And then I expand in alpha, right? So that's how I get this, okay? Instead of, because it would look like I would have a log of a log, right? But I'm using the fact that alpha is small, okay? I'll let you work it out, but that's what the answer is, okay? All right, yeah, I say it right there. Alpha is small, and I've used the property of the natural log of 1 plus some small number, okay? So we've got the natural log, all right? So now we want to compute how this thing or how these things depend on mu, right? So that calls for some differentiation. So taking a derivative, all right? For reasons that will become clear, in a little bit, let's not take the derivative with respect to mu. Let's take it with the derivative. Let's take a derivative with respect to the natural log. Okay. Okay. So if I do that, the left-hand side is what it is, right? And we're saying, by definition, this physical mass cannot depend on mu. All right. So the left-hand side is 0. Okay. The right-hand side is a whole different ballgame. Okay. So the right-hand side, we take our derivative, and what it does is, it splits everything out, nice and neat. Okay. So now I see I've got this term here that's the derivative of the mass with respect to mu, basically. Okay. And I've got some other stuff. So here's the derivative of the coupling with respect to mu. It's multiplying that log that we want to, try to understand or try to cancel off with the dependence of alpha and m on mu. Okay, but at the end of the day, what am I saying here? Assume that is order. Okay, yeah. So this guy, this term here is, I'll show you in a minute. It's order alpha squared. So it's higher order. So we can automatically neglect this. Okay, I'll prove this to you in a minute. Okay, so that means that all that's left is this term, because what happens is this guy, and no. So this guy, oh, yeah, that's what I'm solving for. Okay, so I combine these two and I solve for it, and I end up getting something that looks like that. Okay, so I find that the differential equation that describes how our Lagrangian mass parameter depends on mu looks like this. Okay, and now I could solve it and integrate it, and it would tell me how the mass depends on mu. All right. And this stuff, if you want to be technical, this stuff in the parentheses is called the anomalous mass dimension, or the anomalous dimension of mass parameter. Okay? I don't know where that name comes from or what it means, but that's what it's called. Okay, but this is what this equation is telling us is if we want m physical to be independent of mu, this is how the Lagrangian mass parameter has to depend on mu. Okay, so the next thing you can do is you can compute the residue. Okay, and the residue is given by that equation, so it's a derivative with respect to k squared, or the inverse of the residue. It's a derivative of the exact propagator in the MS bar scheme with respect to k squared. Okay, and you can plug in everything, and you get some residue that looks like this. So it's not 1, right? That's what we originally required, but in this MS bar scheme, we've kind of, filled with stuff. And now our residue is not 1, but it has some order alpha corrections. And you notice it also depends on mu squared. Okay. Right. So we could also, so what we did before, let's see what we did. Yeah, so we used kind of an on-shell scheme when we renormalized, because remember we did the renormalization of the vertex. And there we also had poles and logs of mu, right? And we chose our counter term to cancel off both of those, right? And then we allowed for some constant piece, but then we ended up finding that that constant piece was 0, right? But what we can do is apply the MS bar scheme to that vertex. And in fact, that's what you should do. If you compute the self-energy in MS bar, it doesn't make sense to go off and compute the vertex in the on-shell scheme. Okay, it makes sense to stick with one scheme. Okay. All right. So what we would do is we write our counter term as this. We go calculate the loop, and then we would choose the C parameter and the MS bar scheme to just cancel off the pole. Okay. So what we've left behind is the mu. So remember, this is what we used before. Right? You see they differ by the mu's and the possible constant piece. All right. Okay, so then the MS bar scheme, we're going to have something that looks like that. And if you go back and compare it to what we had before, you'll see the big difference again is the dependence on the log mu. Okay. Right. So let me just go through this real quick, and then we'll take a quick break. Water. Okay, so yeah, so we've gone through this, and now we think we fixed it, right? We're working in the massless limit, and we saw that we were screwing up basically the renormalization, right? We were not doing things correctly. We had kind of ill-defined, conditions. So we've gone back and fixed that. Now we're working in the MS bar scheme, and now what we want to do is say, okay, now let me take the massless limit of my total, or at least the virtual piece, because that's where these logs are coming from. let's take the massless limit and see what happens in this bar scheme. Okay. So we take the massless limit, we get something that looks like this. Remember, we have to account for the fact that the residue is not 1, so that's where these r squared terms are coming in, because we have 4 fields, right? 2 in the initial state, 2 in the final state, and they each carry a factor of square root of r. Okay, so we get r squared, but we can plug in what r is. Remember, r depends on alpha, right? So I can plug in what r is and then expand everything. Okay. And where do I get? I get to something like this. Okay, so this is my amplitude, and then I want to take this modulus. I'm going to take this modulus squared. Remember, it goes like the tree level piece squared, and then the cross term between the tree and the virtual piece, right? And then the virtual piece squared is higher order, so we can drop that. Okay, so this is the cross term, right? You can see it easy from here. All right, so that's what we have for the virtual piece. Well, we don't have to do anything to the real piece. That didn't involve any normalization. So we can just write down what we had there, and we can add the two. Okay? And what happens is we get exactly the same mass dependence. All right, so we here. So here's what we had. Here's the mass dependence we had from the virtual pieces, right? And there's what we got for the real piece. They come with opposite signs, and so when we add them, they actually cancel each other off, right? And so what we end up with is a cross section. Well, the amplitude squared, but it's basically the cross section that doesn't depend on the mass. So we've properly taken care of this mass dependence, the big logs coming from m squared. Right? And so it's well defined in the massless limit. We still have, a couple of things. We have dependence on this unphysical scale, and then we also have this possibly big log from having good detectors. Okay. Right. So it looks like the cross-section depends on mu, right? But the cross-section is unobservable, just like the physical mass is unobservable. So that must mean that alpha has the mu dependence to cancel off that mu dependence. Does that make sense what I'm saying? So we're using the same logic, right? That this is a physical thing. We go off and measure this, and there's no dependence on mu, right? So alpha is the only thing left there that's free, right? Or that we can imagine is free, and so it must have some mu dependence, and that mu dependence exactly cancels that dependence off. Okay. So let's see how. Right. So. So we'll do the same thing that we did before, okay? So we'll this, and then we'll see this as a recipe, okay? So we take the natural log of both sides, okay? So on the left-hand side, I've got the natural log of the cross-section, basically. And on the right-hand side, I've got what that stuff is, right? And C1 and C2 are just pieces that don't depend on alpha or mu. And then I differentiate with respect to not mu, but the natural log of mu. Sometimes you'll see it done the other way. You'll see actual derivatives with respect to mu, but in this case, we'll just do the natural log. All right. So on the left-hand side, I argue again that this thing can't depend on mu. Right? It's physical, so it has to be 0. So that gives me on the right-hand side stuff of some dependence on alpha of mu, and I can solve that. Right, and I have this 1 over alpha here. And so when I separate and multiply through by that alpha squared, I see that the differential equation that tells me how alpha depends on mu starts at order alpha squared. And that's what I told you earlier, that it started at alpha squared. Okay, but this shows you. Okay, and this thing is a very important piece of information. It's called the beta function, and we'll compute the beta function for a lot of theories. Right? It's important because it tells us how the coupling varies with our normalization scale. Okay, so we have to, when we compute things, there's going to always be some dependence on mu, right? And so what you do is you try to choose a mu that it makes physically, it's a physical scale in the process. Right? So if I'm doing, if I'm colliding protons on each other, and I'm trying to make, if I'm doing like Drell-Yan production of, say, like a Z boson, right? So the physical, the large scale there might be the mass of the Z, right? So I might set mu to mz, right? Or in this case where we don't have any masses, so we'll choose mu to be the square root of s, right? That's the only real energy scale we've got, okay? And then what you do is you vary mu, right? You have your cross section, you have your couplings that depend on mu, and you vary mu, and you see how does your cross section, how does it vary? Does it have a wide dependence, right? So you would plot the cross section as a function of mu, right? And you would have something that looks like this, maybe, all right? And then you would vary. You take it, down by a factor of 2, and then up by a factor of 2. All right, and the width of this thing tells you how well you're doing in your perturbative calculation, right? Because if it's really wide, if it has a strong dependence on mu, what does that mean? It means that higher order corrections are really important because we know the cross section can't depend on this. So there's got to be pieces beyond what we calculated that are canceling these off, right? And in fact, a lot of times what you'll see this for next to leading order, and then some smarty pants will come along and calculate next to leading order, and you'll see a band that's skinnier and actually most of the time fits inside of that, okay? And that's the behavior that you want to see, right? You want to see, going from leading order, which is typically like this, right? If you plugged in the running couplings into a leading order cross section, next to leading order brings it way down, the dependence, and then next to leading order, you're really getting close to, almost independent of mu. Right, okay, so let me stop at this slide. Okay, so what you can do is you can actually solve that equation, that differential equation, and integrate it out, and look at this particular case. So we've integrated from mu1, some reference scale. So mu1 might be like the Z mass, right? That's the typical reference scale for LHC type physics, up to some other scale that we'll call mu2, right? And so this equation tells us how alpha depends on mu2, right? And so in this particular case, the beta function is negative, okay? That thing on the left-hand side is the beta function. It's negative. And so when we integrate, it looks like this, okay? And what we see is as we vary mu2, as we make it larger, what happens? The coupling decreases, right? So this is what's called asymptotic freedom, right? So you have a coupling that depends on scale, right? So you can imagine plotting, not the cross section, but the coupling. Right? And what you have is you see that, here's my reference scale, let's call it mz, okay? And as I vary mu up to higher scales, this thing falls off. I don't know if that's the correct dependence, but it falls off, right? It usually looks like that, okay? What happens as mu decreases? Well, as it decreases, you're going to get what? This part, the denominator, is actually going to get smaller, right? And the theory becomes more strongly coupled. In other words, the coupling ramps up as you go down in energy, okay? In other words, you're going to hit some point where this thing is, on the order of 1 or larger, okay? And at that point, that's telling you that your perturbation theory is breaking down, right? Because now alpha squared is not going to be some smaller and smaller number. It's going to be a bigger and bigger number, right? And so at that point, you say, oh, I got to cut it off, okay? And this is actually the case for QCD, right? So we've computed a nice, little scalar theory, and computed the beta function, and we see this behavior. So we see the coupling dies off at high scales, but it gets very strong at low scales, right? And so this is the actual mechanism behind the behavior of quarks and gluons, right? So at low scales they bind together, right? But at high scales the coupling gets small, okay? So at large scales you're safe in using perturbation theory, okay? This is basically what it tells you, all right? And the prime example of this is, like I said, QCD works like this. QED is the exact opposite. So it gets smaller as you go down in energy, but it gets larger as you go up in energy. Okay? And so you can see here's one case where you've always been taught that alpha is equal to 1 over 137, right? But if you actually compute this thing, the corrections to it, and you look at it as scale of the Z boson mass, you actually find that it's 1 over 128. Okay, so that's the prime example of that. Okay, so let me take like a 2-minute break and just to get a drink of water. Do you guys have questions about that?
No.
Before? Okay. All right.
We said factor of energy.
It has units in it.
I think that's the opposite for quarks. As they are near together, they have small couplings. As we increase the energy,
Right.
it means that they're making them separate.
No. As you increase the energy, you're probing them at a smaller and smaller scale.
Okay.
Yeah. So that's what we're talking about this week. Yeah. So you can think of it as going down in energy. That's like when you try to separate them, right? You try to separate quarks, and you can't. They start all kinds of weird stuff starts happening. All right. Okay. All right. So just to summarize that whole thing, okay? So we were trying to deal with these large logarithms that we had from the virtual corrections. We saw that they were partially canceled from the real corrections, but not completely. And so we had to go back and review our approach. And so what we tried was to just cancel the poles when you were normalized, and that's called the MS bar scheme. And the consequence of that is that you get something that you cancel. It's simple because you're just canceling off the poles, but you're not canceling off that fake normalization scale, that mu, right? And so how do you deal with that? Well, you deal with it by saying that anytime you compute an observable, it can't depend on an unphysical scale. Did you bring cookies for everybody? Or?
It's mine. So many troubles. And it's all melted.
So we argue that observables have to be independent of the scale, right? So that means that the only possibility is that parameters in our theory must depend on mu, okay? Right, and so we did that for the mass, we did it for the cross-section, right? And we found that, sure enough, the mass and the coupling satisfy these kind of differential equations that tell us how they depend on mu, right? The anomalous mass dimension goes like order alpha, and the beta function goes like alpha squared.
You're saying that these calculations are through for both QC and QED.
Yeah, you do the same thing in QED and QCD. The difference between those two is that in QED the beta function is positive, but in QCD it's negative. So anytime you can compute a beta function, you see negative, you know it's has asymptotic behavior or asymptotic freedom.
Here it's negative, you know, it can be positive.
Yeah, it can be positive depending on the theory. Yeah. We'll see that next semester. Because what we're going to do now is I'm going to develop basically a recipe of how to compute these things. Okay, we won't have to do all that stuff. Okay, and that's exactly what we're going to do here. Okay, so I'm going to basically, like I said, give you a recipe on how to compute this, how to compute these, the dependencies of parameters on this unphysical scale. Okay, these go by the name of normalization group equations, or RGEs. I don't think it has anything to do with group theory. I don't know. I think it's just a group of equations. But anyways, they're called RGEs, okay? And I can't remember why. All right? So the way you start is you write the Lagrangian in two ways, okay? You write the Lagrangian and the bare Lagrangian, right? And Baire Lagrangian, you know it's the Baire Lagrangian because I put zeros on everything, right? The counter terms, the fields, okay? And the Baire Lagrangian is what it is, okay? And then you can write the renormalized Lagrangian, right? So here I've introduced the renormalization constants in front of the kinetic term, the mass term, and the coupling, right? And you see that I'm working in d equals 6 minus 2 epsilon dimensions in general. So that's why this mu appears here. Right? So I've already put the mu in. I've already rescaled g so that it's has mass dimension 0. Okay, that's the starting point. So you write your theory down in bare form and then the normalized form. Okay, and then what you do is you look at those, you compare those two, and you can read off relationships between fields or masses or couplings in the bare case and the fields and mass and couplings in the renormalized case. Okay? So if you look, and let's see, you compare this guy, right? So I look at this is a constant, right? So this is telling me that phi 0 must be equal to phi times z phi to 1/2 square root, right? Okay, and so that's what I get. Okay, so I get this relationship between the two fields. Then I can go and look at the other terms. So I go and I look at the mass terms. I go and look at the mass term, right? And I see that there's some dependence on Zm, right? But I have to account for the fact that the phi, has this z phi, right? And so I have to, when I write down the relationship, I have to basically subtract off that z phi. Okay, so that's where the z phi comes in the relationship between m naught and m, right? And then you do the same thing for g naught. You see it depends on mu, and I'm subtracting off 3 factors of the field because I have 3 fields coming into that vertex, right? And then finally, the guy that we use to kill off the vacuum contribution looks like that. Okay. Okay. All right, so we've done two steps. One, write down the Lagrangian in two ways, and then two, write down relationships between the parameters and couplings and all that stuff between the two. Okay. Now we're assuming that we're using MS bar. Okay, so basically from now on we'll always use MS bar. Okay, so that means that our counter terms are only going to cancel off the poles, right? So they're not going to have dependence on mu or anything else, right? And so this is kind of a disclaimer. So far, and what remains of this class, we'll always only encounter with single poles, right? But there are cases, in particular in QCD, when you calculate real corrections. When you calculate. You get it from virtual corrections, but you can get double poles. So you get like 1 over epsilon squared terms. Okay, so those things are possible. So it's not always just single poles. Okay, so in general, our renormalization constants look like this. They always come with a 1, right? And then we're going to allow for the existence of higher poles. Okay, so we'll write it as 1 plus some constant, and then over epsilon to the n. Okay, so the first term would obviously be single pole. Okay, and the same thing for ZG. Okay, and we've actually already computed this, right? So if you go and you compare these general expressions, and you just set n equals to 1, you can extract what those coefficients are. For our case, the phi cubed theory, right? And for A1, you get minus A over 6, and both B and C are just minus alpha. Okay? All right. So, we all know how much work went into computing these things, right? And so what we're after is a way to basically compute higher order corrections to these guys, to the renormalization constants, without having to compute multi-loop diagrams, because multi-loop diagrams suck. Okay, multi-loop diagrams are really hard. Okay, and we can do this using the same trick that we used on the mass parameter and the cross section. Right? We can always argue that our Lagrangian parameters, either the mass or the coupling, they have some mu dependence. Right? So if we compare things in the Baire theory, the parameters and the fields don't have any dependence on the mu scale, right? It's exact, okay? So the parameters in that theory don't have dependence on mu, but in the renormalized case, we know that they do, right? And so we'll use those relationships. This is some kind of overview. So that we'll use these relationships, and then we'll use that kind of recipe that we applied to the mass and the cross section. All right, so let me show you how it works. Okay. Yeah, this is just arguing. So this just summarizes everything that we've done in the past. So we're arguing that if we have something physical, or in this case, something that's exact, right, that's computed to all orders, the Baire Lagrangian parameters, that it can't have any mu dependence. Okay, and so to account for that, when we use these relationships, we'll let alpha and the mass have some mu dependence. Okay, and that's what we're after. Okay, so let's start by computing the mu dependence of the coupling. In other words, the beta function. Okay, and so typically you would start, and you'll see if you look in Srednicki, you'll see it both ways. You would start with this relationship. Okay, and the first thing we did was what? To both sides? Take a natural log, right? Take a natural log. That lets you separate some of the stuff on the right-hand side. Okay. But first, what we'll do is not work with G. We'll actually work with alpha. Okay, so we'll just convert it. Right. We'll square both sides of our relationship, and we'll divide by through this annoying factor of 4 pi cubed. Right, and that allows us to define alpha. Okay. So what I get is a relationship between alpha in the bare theory and alpha in the normalized theory. Okay. And for future convenience, so we're going to take this natural log and we're going to group the counter terms in one natural log. Okay, we're going to call this function g, and remember it's a function of alpha, but it's also a function of the poles, right, or the epsilon parameter. Okay, and so what you can do with these guys is you can actually use some expansions. All right, so for the time being, just assume that epsilon is not small. Okay, that it's just a constant. Okay, and then we know that these coefficients depend on alpha. So if I go from here, I plug in my expressions, my general expressions for z phi and zg. I get something that looks like this. And then I just start expanding because I'm assuming that this guy is starting at order alpha. Okay? So I just expand that stuff and I get down to that, and then I can expand that log. And so it tells me that this g alpha epsilon, I can write it like this. It's just an expansion in the poles. Right? Everybody get what I did? So I'm taking the natural log of both sides. I haven't done it yet, but I will get the natural log of this guy. Okay. And then I plug in these general expressions that we had for z phi and zg. So there's z phi, goes like 1 plus a over n, zg goes like 1 plus c over n, or cn. Right? And you can see here. Right? So at that point, now I say, let me forget about epsilon being small. Let me just say it's a constant. And let me expand because I know that A and C, they both start at order alpha. So I just do a series of expansions. Okay? Good? All right. Okay? And so what we see is that G, we can actually write it as an expansion in the poles with some coefficients, and those coefficients depend on alpha. Okay, so I'm making a change from a function that depends on alpha and epsilon to a function that just depends on alpha. Okay? And so I look up there, I do some matching, and I see that G1 is just 2C1 minus 3A1, and I know what those are because we already computed those. Right? So I just plug them in, and I get G1 of alpha is minus 3 halves alpha. Okay? That'll come into play in a minute. Okay? That's just doing a little prep work. Okay? All right, so we'll go back to equation 51, which was our relationship between alpha naught and alpha, and we take the natural log, both sides. Okay? So on the left-hand side, I've got the natural log of alpha naught, and on the right-hand side, I've got that G thing, I've got natural log of alpha, and then I've got this epsilon natural log of mu twiddle. Okay? And then our next step is take a derivative with respect to natural log of mu. Okay? We do that on the left-hand side, and we say, okay, this is a bare parameter. It cannot depend on mu, so that must be 0. Right? On the right-hand side, I get the derivative of g. I get the derivative of, so this is using the chain rule because it depends on alpha, and alpha we know depends on mu, right? So there's going to be some term here, d alpha d mu basically. And then here's the derivative of that guy, right? And then finally the derivative of this thing, so it's mu twiddle, but I'm taking a derivative with respect to mu. But remember those two only differ by some weird factors of e to the gamma over 2 and the square root of 4 pi. Right? Do you remember that? You guys remember when we made this change? So in essence, the derivative of mu twiddle with respect to mu is just 1. Okay. Right. So so that leaves us with this epsilon here. Okay. All right. So what do we do next? So we can group together the terms that have, that contain the derivative of alpha with respect to mu. And I've multiplied through by a factor of alpha because there was a 1 over alpha here. Right? So that term epsilon gets an alpha. Okay. And now I can plug in my expression for GA epsilon, right? And GA epsilon was the one that, it's an expansion in the poles. It has some coefficients that depend on alpha, right? And I'm taking a derivative of that with respect to alpha. And so the only thing that depends on that are these coefficients. Okay, so that's what the primes are. The primes are derivatives with respect to alpha. Okay. And then, okay, so here's, again, we use some physical reasoning, or, some, I don't know what you can call it. Let's call it physical reasoning, okay? So this thing represents the rate at which alpha changes, right, to compensate for a small change in mu so that the Baire parameter doesn't change, okay? So if this is, I don't want to say this. So if this, if that's true, it must mean that these guys conspire. So you assume that these guys conspire to basically cancel each other off, right? So that this guy has some term that goes like order epsilon, right? So it gives me a single pole which cancels off that guy. And the next term has a double pole which cancels that, and then blah, 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 blah. You go on down the chain, okay? So you say that, okay, by physical reasoning, that stuff in the parentheses just has to be 1, okay? If you don't believe me, just get it out. No, I'm just kidding. It's just, you want your theory to be well behaved, and you don't want any divergences. You want it to be finite. So that's why I had to argue that these guys have that behavior. Okay. So in other words, this rate, the beta function basically has to be finite as epsilon goes to 0, because we want a renormalizable theory. And at most, it can start at order epsilon to the 0, so epsilon to the first. Okay. And so that means that we should have, what am I doing here? Yeah, so it starts at order epsilon 0, and so what we're going to do is call that thing beta, and we know that it's going to depend on alpha, right? And then I've got a choice on the order epsilon term, and I can choose it to cancel off that dependence that's in equation 58 or 59. Okay, because in the end I'm taking epsilon to 0, so it doesn't really matter. But as a matter of bookkeeping, I can define it to be whatever I want, and I can define it to cancel that stuff off. Okay, so I'm arguing that this stuff is 1, and that this thing has to start at order alpha, or order epsilon to the 0. Okay, and it's some quantity, depends on alpha. We don't know what it is, right? But I'm going to call it beta. Okay, so this is beta, and it depends on alpha. Okay, so what am I doing here? I'm taking that stuff. What am I doing here? So it looks like I'm okay. Yeah, so I'm taking equation 59, right? And I'm moving everything over to the right-hand side. And then I'm plugging in. There's no change from the first line to the second line, is there? Okay, good.
The sign has changed.
Oh yeah. Okay, so it's a typo. So going from there to there, I shouldn't have that -1.
Okay.
Okay, so I've expanded. Thanks. I would have never figured that out. Okay. And so again, so at this point, what we argue, because remember, this is the stuff in the parentheses, and we argue that it has to be finite, right? And so at most, I'll get, some term that goes like alpha G1 prime, right? The pole part of it is going to cancel off. Oh, no, actually the pole part cancels off because I have an epsilon out front, right? So that cancels that off. So that means I get this contribution, and then everything else is going to be finite. It's going to be higher order, but it's going to be finite. Okay, that's what we're arguing because we want a renormalizable theory. Okay, and so at this point we can plug in what we have for G1 because remember this is the G1 of alpha. Okay, and remember that G1 of alpha was just minus 3/2 alpha. Right? So when I take a derivative, so what are we doing? So we're plugging in our early expression for G1 and compare it to equation 60. So this is what we got from the theory, right? This is what we argued, okay? So the two different things. So here's what we got from the theory. This is what we're arguing that this thing has to have a form of. It has to start at order epsilon 0. No poles, okay? And so now we compare those two equations, right? And I'm able to write down this beta function. So the beta function is just this piece, right? And beta, or G, we said what G1 was is minus 3/2 alpha. So you take a derivative with respect to alpha, and you're left with minus 3/2 alpha squared. Right? And if you go back and compare that to what we got from the calculation of the cross section, you remember how much work that was, right? You find that you get the same thing, the beta function. Okay, so the moral of the story is, if you want to know, how the coupling behaves as a function of your unphysical scale, you don't have to go and compute the next leading order cross section for some scattering. You can just calculate. You can just renormalize the theory, which involves, calculating the self energy and calculating the vertex. Okay, does that make sense? And then follow this recipe, because that's all we did in this second part. Right? I just wrote down the Lagrangian in two different ways. Wrote down relationships. Write down relationships between those two. Take a natural log derivative. Use some arguments along the way about, you want your theory to be renormalizable, so it has to start at order epsilon to the 0 at most. It can't have any poles, right? And then you go and you plug in what you got for the counter terms from normalizing the self energy and the vertex. And that will allow you to extract the beta function. Okay? All right, so it's a well-oiled machine, The hard part is calculating the loops. Okay, I'm going to stop there because I'm crapped out. But we'll pick it up. There's a couple more parameters that you can calculate the mu dependence of, and we'll do that. I'll show you. We'll use the same recipe as we just did. And then after that, I don't remember what we're doing. So I have to figure it out. Okay? You guys have any questions about this? The notes the slides are on the website. So have a look, and if you have questions or anything, let me know. As far as I said I was going to say something about the exam. I'll just send out an email. I'll just explain it in an email. Okay. I just noticed a couple, more than a couple, ones that turned in that I think that it's just a misunderstanding of either what I'm asking or just how to apply, Feynman rules. Okay, so I'll send it out, and if you guys have questions about it, let me know. Okay.
Okay.